one sigma. This sigma bond is formed by the overlapping of sp2 and this carbon and nitrogen is formed by the overlapping of sp2 and the s structure of alkane. Now in this structure of alkane, now you see here this carbon and the carbon, one sigma bond. This is a sigma bond. It is formed by the overlapping of sp and the sp.
Hello my dear friends, I welcome back you to my YouTube channel, that is Beginners Chemistry, where you can learn the chemistry in the easy manner. In our basics of organic chemistry, we have studied in our last class, that is VBT, and we have studied about the overlapping, how the sigma bond will be formed, how the pi bond will be formed. Now how the sigma bond and the pi bond will be formed for the O2, and how the sigma bond and the two pi bonds are forming for the N2, that we have seen in our last lecture. But when the same overlapping and the VBT concept, if we have applied for the CH4, it is not applicable for the CH4. Why? As per the VBT, it should give the only two bonds, but experimentally now we are seeing that carbon, it is having the four bonds. Now why it has failed and why the concept hybridization we are going to study in this lecture. Now what is the reason behind the hybridization? Clear? That we are going to study in the lecture. Now let's start our lecture. Now before going to start our lecture, I just want to give you the quick recap of the last lecture what we have studied. Now in the last lecture, the first we have studied bond formation, taking the example of the H2. Now potential energy versus radius, done. Now if the two hydrogen atoms are at the infinity distance, its potential energy formula K is equal to Q1 charge of cation, charge of anion by radius. If the radius r is equal to infinity, potential energy is equal to 0, done. Now as we are decreasing or when the two hydrogen atoms are attracting, its potential energy is decreasing, and they have overlapped some region of one hydrogen atom and another hydrogen atom. This region we call it as a overlapping region, and here this nucleus and this nucleus, and length we call it as a bond length. Still if you want to decrease this bond length, what happens? The potential energy will be increased. Potential energy will be increased means every molecule want to be attain the stability. If you and that it will be attained and it will be formed the bond at a certain bond length. If that certain bond length, if you want to decrease, still if you want to decrease that certain bond length or stable bond length, what it will happen? That bond will be broken out. How it will be broken out? Due to the electron repulsion and this positive charge nucleus and the nucleus repulsion. Due to that, what it will happen? Bond will be broken out. Clear? And here they have shared some region, right? And this we call it as a, which one? This we call it as a overlapping region. Clear? Then after that we have studied about the shapes of the orbital. Now shapes of the orbital, we know that s orbital shape is a spherical. Now in this spherical region only we can find the electrons in the which one? S orbital. Now we know that shape of the p orbital is dumbbell. Now in this dumbbell region only we can find the electrons in the p orbital. Now we have studied about the one concept called the directional or the non-directional. Directional means only in the one. If you want to find the electron in the 3D space, if you go it for the z-axis, and if you go along the x-axis, if you go along the y-axis, done. Clear? Now this is a 3D region. We are having the three axes z, y and the x. Now if only in one region or if you only in the one axis if you are getting the electrons, that we call it as a which one? Directional. If in all the regions or if in all the axes if you are getting the electron, that we call it as a non-directional. For the s orbital, you can see if you go along the z axis you are getting the electron. These white ones are the electrons. Now if you go along the x axis you are getting the electron. If you go along the z axis you are getting, if you go along the y axis you are getting the electrons. Now if you go along this axis also, you are getting the electrons. In the all the direction you are getting the electrons. That's the reason s orbital is non-directional in nature. S orbital is non-directional in nature. Now comes to the p orbital. P orbital, if I go along the z axis, I was not getting the any electron, I was getting only the nucleus. Clear? If I go along the x axis, I was getting the electron. Now if I go along the y axis, I was getting only the nucleus. I was not getting the any electrons, or I was not touching any lobes. Clear? Now you see, p orbital is directional in nature. Then after that we have studied about the internuclear axis and the overlapping internuclear axis. As per the NCERT, internuclear axis we have taken it as a Z. Then after that we have studied about the axial overlapping. Axial overlapping leads to give the sigma bond, and the sideways overlapping leads to give the pi bond. Axial overlapping leads to give sigma, sideways overlaps leads to give the pi. Done. Now in that we have studied about the SS overlapping first. SS overlapping, this is s orbital. This s orbital overlaps leads to give the sigma bond. Now sigma bond will be in this manner. Clear? Now this is the electron and this is the electron. Now this is the nucleus of one s orbital, this is nucleus of the one s orbital. Now you see, electrons are very nearer to the nucleus. That's the reason sigma bond is stronger than the pi bond. Why it is stronger than the pi bond? Now I will explain when we study about the pi bond. Then this is S and the S, or 1s are the S and S. Now comes to the p orbital case. Now when it comes to the p subshell, it is having the 3 orbitals, right? 3 orbitals. What are there? One is px, one is py, one is pz. Done. Now in the 3D space, if you take this as a nucleus, now this is a pz orbital. Done. Now for the pz orbital, px orbital is perpendicular. This is a px orbital. Then py orbital is also perpendicular to the other two lobes, other two p orbitals. Means all the p orbitals are perpendicular to each other. Then if I was taking the internuclear axis Z, then pz orbital and the pz orbital overlaps leads to give the which one? Sigma bond. Clear? Now this is a one pz orbital. Now this is one pz orbital. These two overlaps leads to give the sigma bond. That I was explained very clearly in the last lecture. If you have missed the last lecture, better you go and see the last lecture, and if you see this lecture, it will be connectivity of the last lecture. Then only it will be understand for you. Then next I was consider the INA, internuclear axis, is equal to Z, right? Then in this internuclear axis Z, this is a Z. On the Z axis we are not having any electrons. Then if I was consider the px orbital, this px orbital is perpendicular to the internuclear axis and it is having the electrons. Clear? Then pz orbital is not having any electrons, and the px orbital we are having the electrons. Now this px orbital sideways overlaps leads to give the which one? Pi bond. It leads to give the pi bond. Now here the electron density will be high in this pi bond here. Electron density will be high in the pi bond. Now you see, this nucleus and the electron is far away from, right? Nucleus and the electrons are far away from them. So the nuclear attraction between this electron and the nucleus is less. That's the reason compared to the sigma bond, you can see here the sigma bond, this electron and the nucleus is nearer. So the attraction between the electron and the nucleus will be high. That's the reason the sigma bond is stronger. But when it compared to the pi bond, this nucleus and the electron distance is far away from them, then the nuclear attraction between these two will be weak, and that's the reason the pi bond is weaker compared to the, which one? Weaker compared to the sigma bond. Now we got to know that if the internuclear axis, if it is Z, internuclear axis if it is Z, always s orbital plus s orbital overlaps leads to give the sigma only. Here s orbital is non-directional, in the all the direction you will get the electron. Then if the pz orbital plus pz orbital overlaps leads to give the sigma bond. As per the NCERT, Z axis only they have considered, so we are also considering it as a Z only. Then px orbital and the px orbital. This px orbital is perpendicular to the internuclear axis, that we have considered it as a Z, then leads to give the pi bond. Then py orbital plus py orbital overlaps leads to give the pi bond. Sir, then what about the other axis? If suppose if they have given in this manner, pz orbital plus one px orbital, pz and the px orbital leads to give the no bond or no bond formation or the zero bond formation or zero overlapping. Why? Because one pz orbital will be in this manner, pz orbital electron will be in this manner, and the px orbital electrons will be in this manner. Now here how they will overlap? They cannot overlap. You can see here the electrons are in this, one electron is in the parallel, one electron is in the perpendicular. How they will overlap? There is no overlapping. If without overlapping, there is no any bond formation will be happen. So pz and the px orbital overlaps leads to give the no bond formation, zero bond formation. Is it clear up to now? Now then after that we have studied about the how O2 is having the one sigma bond and how the O2 is having the one pi bond. That formation of O2. In the formation of the O2, in this formation of the O2, we have studied what? Valency electrons of filled orbital electrons will participate in the bonding. Electrons which are not participated in bond formation is called as lone pairs. If any electrons has not participated in the bond formation, those electrons we call it as a lone pairs. Now you see for the oxygen, two oxygens we are talking, right? One oxygen and the one oxygen. One oxygen electronic configuration is 1s2, 2s2, 2p4. Then another oxygen 1s2, 2s2 and the 2p4. Now what I said, valency electron will be participated in the bond formation means 1s we can cancel out. Then this s orbital we are having the 2 electrons. Now for the p orbital, if you take this as a 2px, 2py and 2pz, and 2px we are having the 2 electron and 2py and the 2pz we are having the 1 electron. Now comes to the again here 2s, next 2px we are having the 2 electron and the 2py and this is a 2pz. Now what I was considering here, the INA internuclear axis I was considering it as a Z. Clear? One oxygen Z orbital we are having the 1 electron, pz orbital we are having the 1 electron. Now you see next py orbital also we are having the 1 electron, py orbital is also we are having the 1 electron. Next another oxygen also pz orbital we are having the 1 electron and they will overlap along this internuclear axis. Done. See this along the internuclear axis pz orbital overlaps leads to give which bond? Sigma bond, and one bond contain 2 electrons, right? Then this another oxygen also py, we are having the 1 electron. This py sideways overlaps leads to give which bond? Pi bond. So that's the reason oxygen it is having the 1 sigma bond, and it has formed by the overlapping of pz. Now it is formed by the overlapping of py. Done. Then you see these two electrons, px electrons and 1 s electrons has not participated in the bonding. So that's the reason we call this as a lone pairs. That's the reason oxygen it is having the 2 lone pairs. Done. Next comes to the N2, nitrogen and the nitrogen. One nitrogen we are having the 1s2, 2s2, 2p3. Another nitrogen 1s2, 2s2, 2p3. S cancel. Then this s orbital we are having the 2 electrons, and the p orbital we are having the 3 electrons. Now this is 2px, 2py, 2pz. Here also s orbital we are having the 2, and p orbital we are having the 3, that is 2px, 2py and 2pz. Done. Now internuclear axis I was considering it as a z. Then internuclear axis if I was considering it as a z, now pz orbital 1 electron, better I will go with here. Now here this is a 1 nitrogen pz orbital, we are having the 1 electron. Another nitrogen pz orbital we are having the 1 electron, and they will overlap in this manner. Done. This is a pz orbital. Then after that we are having the py orbital. Now py orbital of 1 nitrogen we are having the 1 electron, py orbital of another nitrogen we are having the 1 electron. This sideways overlaps leads to give the pi bond. Then after that, then next px orbital of 1 nitrogen we are having the 1 electron, and the px orbital of 1 nitrogen we are having the 1 electron, and these also sideways overlaps leads to give the pi bond. Clear? Now this is the formation of the N2. Now you see in the nitrogen we are having the triple bond. One is a sigma bond, and the remaining are the 2 pi. This is the formation of the N2. Clear? Next, if the formation of the CH4, if you want to see the formation of the CH4, according to the VBT, formation of the CH4 it has been not explained. Why it has been not explained? Now you see carbon. Now it is having the valency electronic configuration is 2s2 and 2p2. Then as per the VBT, what I said, now valency electron of field or the orbital containing half filled electron, then that only will be participated in the bond. Now you see as per that one, then carbon should form the only 2 bonds. But we know that carbon is forming the how many bonds? Carbon is forming the 4 bonds. That it was been not explained by the VBT. Now it was explained very clearly by the hybridization. Now we will start the concept called the hybridization. Now we'll see the hybridization. Now hybridization is one type of the hypothetical concept. Whether the hybridization is happening between the molecules, that we don't know, but it is providing the molecular geometry and the shape. Now it is providing the molecular geometry and the shape of those molecules. Now best example that we are going to start with the CH4. Now what is the shape of this orbital and what is the geometry of this CH4, that we are going to study. First of all, what we have studied, we are going to see carbon. Experimentally we have found that carbon and these hydrogens are having the bond angle of 109 degree 28 minutes. Here this we have found experimentally. Then how this hybridization is helping How this carbon and hydrogen is having the 109 degree 28 minutes bond angle between the carbon and hydrogens? Now, first we know the ground state electronic configuration. First, what I was writing, ground state electronic configuration of the carbon, because the carbon is the central atom. Ground state electronic configuration of the carbon and valency electrons only will participate in the bond formation, already explained very clearly. Then valency, ground state valency electronic configuration of the carbon will be 2s2, 2p2, 2p2. Then as per this VBT, this carbon should form the two bonds. Then, but here when the four hydrogens are forming or try to form the bond with the carbon, here how many hydrogens are formed the bond with the carbon? 4. But as per the VBT, carbon can form only the two bonds. Done. And the remaining two unbonded hydrogens are also want to try to attain the bond formation with this carbon. So what these hydrogens will do, these bonded hydrogens will repel this hydrogens. Clear? Now here already this carbon has formed the four hydrogens are coming to form the bond formation. Now listen, four the hydrogens are coming to form the bond formation towards carbon. Carbon has formed the two bonds with the two hydrogens, and remaining two hydrogens, unbonded hydrogens, are also want to try to form the bond. But this bonded hydrogen, what it will do? It will repel these two hydrogens. Due to that repulsion, what it will happen? Energy released. Due to that repulsion, due to this bonded hydrogen, when they are repelling this hydrogen, energy released. That energy is utilized by this central carbon. That energy, repulsion energy, is utilized by that central carbon. What that it will do? It will excite one electron. By utilizing the energy only, electron will be excited to the next level, right? Clear? The same thing, it will excite this electron to this empty orbital. This will be excited to the empty orbital. So this is a excited state electronic configuration of the carbon will be now 2s1, 2p3, 2px1, 2py1, 2pz1. Clear? How this carbon has been excited this electron? First it has formed the bond with the two hydrogen, and the remaining two hydrogens are also want to try to attain to form the bond. But this bonded hydrogen are repelling. Due to that repulsion, energy released. That energy has been utilized by the central carbon. In this central carbon, this 2s electron will be excited to the empty orbital of the 2p. This is a excited state electronic configuration. This is called as a excited state electronic configuration. Now, when this excited state electronic configuration, if the orbitals want to be hybridized, all the orbitals should be in the same energy. If the orbitals to form a bond, what it should be have? It should have the same energy. We should have the same energy. Then what we are making here, in the excited state carbon, it is having the 2s and the 2p, we are having the 3 electrons, right? Then what we are doing to make all the orbitals energy same, we are intermixing. So intermixing of the atomic orbitals. What is the definition of the hybridization? Intermixing of the atomic orbital leads to give the new type of the hybridized orbital is known as the hybridization. So to form the bond formation, all the orbitals should have the same energy. So this 2s and the 2p almost it will be present in the same shell, right? 2s and the 2p. Almost it is having the slight energy difference, but it is having the same energy. So that's the reason it will intermix. This s orbital and 3p orbital. Now p orbital dumbbell, right? This 3p orbital. What it will happen? This 3, one s orbital and the 3, which one? p orbitals intermix leads to give the new hybridized orbital. So this all will intermix leads to give the one new type of the hybridized orbital. Now the hybridized orbital representation will be in this manner. One lobe will be higher and the another lobe will be smaller. Clear? Now one lobe will be higher and the another lobe will be smaller. And the one lobe will be higher and the another lobe will be smaller. And the one lobe will be higher and the another lobe will be smaller. Clear? Now how many hybridized orbital we got totally? When these 1s and 3p orbitals are intermixing, then we got the 4 new hybridized orbital. How many? 4 new hybridized orbital. 4 new hybridized orbital we got. These 4 new hybridized orbitals now should arrange themselves in such a way that it should be free from the repulsion. So when these 4 hybridized orbitals, what it should be do? This, when the carbon has been excited, then after that what it should have to form the bond formation, all the orbitals energy should be same. So that's the reason what we did, we have intermixed these 4 orbitals. Which one? 1s and 3p orbitals. When they have intermixed, leading to give the which one new type of the hybridized orbital. This s orbital and this total this 3p orbital hybridized or intermixed leads to give the which one new type of the hybridized orbital, right? These 4 new hybridized orbitals should arrange themselves in such a way that they should be free from the repulsion. They should be free from the repulsion. Then this new 4 hybridized orbitals arranged themselves at the bond angle of how much? 109 degree 28 minutes. At the bond angle of 109 degree 28 minutes, when they have arranged, they are free from the repulsion. They are free from the repulsion. Clear? Now when they have arranged at the bond angle of how much? 109 degree 28 minutes, all these 4 new hybridized orbitals are free from the repulsion. Done? Now you see, you can see each hybridized orbital we are having one electron, right? Each hybridized orbital we are having 1 electron. See, this is excited state electronic configuration. When they are intermixed, they formed the new hybridized orbital. New hybridized orbital, each new hybridized orbital we are having the 1 electron. Then here also, then they have arranged themselves at the bond angle of 109 degree. They are free from the repulsion. Now each hybridized orbital we are having the 1 electron. Done. Then after that we are having the 4 hydrogens, right? Hydrogen electronic configuration is 1s1. So that in the s orbital we are having the 1 electron. So this new hybridized orbital, now this new hybridized orbital and 1 s orbital will be overlap, and new hybridized orbital and hydrogen or s orbital will overlap in this manner. Now this is a molecular geometry of the which one? CH4. See, in this manner this is bonds has been formed. Here the carbon and the hydrogen, and here the carbon and the hydrogen, here the carbon and the hydrogen, here the carbon and the hydrogen. So here what they will ask you, you know, this carbon and the hydrogen, this carbon and the hydrogen, this carbon and the hydrogen, and this carbon and the hydrogen, it has been formed, right? Now what is the bond angle between them, they will ask. What is the bond angle between them, they will ask. Here the bond angle between them, it is 109 degree 28 minutes. Done. Then they will ask you what is the overlapping, what is the overlapping between this carbon and the hydrogen, they will ask. The overlapping between this carbon and the hydrogen, this carbon hybridization is sp3 and this orbital is present in s. So this bond is formed by the overlapping of sp3 and s. sp3 and s. Clear? Then here this carbon hybridization is sp3. Sir, how this carbon hybridization sp3 it has came? Now you see. Here how many orbitals are intermixed leads to give the new hybridized orbital? 1s and 3p, right? 1s and the 3p orbitals only intermixed leads to give the sp3 hybridized orbital. So these orbitals we call it as a which one? sp3 hybridized orbital. sp3 hybridized orbitals. Clear? In this manner, sp3 hybridization has been killed. In the same way, how the sp hybridization, how the sp2 hybridization, and how the sp3 already I explained. Once again I will explain. Now, how it will be related with the organic, sir? Now, we know that ethene are alkyne hybridization between this carbon and the carbon is sp. Now, if you talking about the alkene, now carbon and the carbon hybridization is sp2. Now, next one we are having the ethane, carbon and the carbon, it is having the sp3. So to understand what is the hybridization between, how the hybridization, how they are forming, first of all we have to understand how the sp hybridization is forming and sp2 hybridization is forming and how the sp3 hybridization is forming. Now we have to see. First we will go with the sp hybridization, or first of all I want to give you the basic definition of the hybridization. What is the basic definition of the hybridization and what are the points you have to remember for the hybridization? What are the points and what is the basic definition of the hybridization? Now we'll say, what is the meaning of the hybridization? Intermixing of atomic orbitals. Intermixing of atomic orbital overlaps leads to give the new orbital. Intermixing of atomic orbitals overlaps leads to give new hybridized orbitals. Overlaps leads to give the new hybridized orbitals is known as a which one? Hybridization. Is known as a hybridization. Clear? Now, first one, what happens here? First point you have to remember, orbitals have slight energy difference. Slight energy. If the orbitals are having the slight energy difference, then they can excite the electrons to the empty orbital. Second point you have to remember, central atom provides required orbitals. Central atom provides required orbital to the hybridization. To form the hybridization, central atom will provide how many orbitals it will be required. Clear? Then third point, number of orbital produced after the hybridization are equal to the number of orbital participated in the hybridization. Means here how many orbitals participated in hybridization leads to give that many hybridized orbitals. So if one s orbital, one p orbital intermix leads to give the sp hybridized molecule. Clear? Then if 1s 2p, if it is intermixing, then leads to give the sp2. 1s and 3p intermixing, it leads to give the sp3. Clear? Done. Next point, this is very, very important. All the hybridized orbitals are identical in shape. So you can see here the one s orbital and p orbital, normally it will be in this shape. When the electron is excited, for the carbon just now we have seen, for the 2s orbital and for the 2p orbital, now this is a p, done, and this is a s. When they are intermixing, leads to give the hybridized orbital, right? Hybridized orbital shape will be in this manner. one lobe will be higher, another lobe will be smaller. One lobe will be higher and another lobe will be smaller. One lobe will be higher, another lobe will be smaller. Clear? In this manner, the hybridized orbital will be there. Done. Now this hybridized orbital energy and shape should be same. Clear? It should have the identical. This hybridized orbital will have the identical shape and size and energy. Is it clear? This newly formed hybridized orbital will have the identical shape and it is having the size and it is having the same energy Clear? Now we'll see how many orbitals intermixing leads to give the sp, how many orbital intermixing leads to give the which one, sp2. Now how many orbital intermixing leads to give the sp3. Now we'll see. First example, I was explaining sp hybridization. In this sp hybridization, how many orbitals are intermixing? One s and one p orbital is intermixing. One s and one p orbital is intermixing. One s and one p orbitals are intermixing. When these two orbitals are intermixing, now what we will get? We'll get the two new hybridized orbital will get, right? How many atomic orbitals are intermixing? The same, that many new hybridized orbitals will be formed. If here 3 it is intermixing, 3 new hybridized will be formed. If the 4 new hybridized will be formed. Here only 2, right? One s and one p. Clear? Now hybridized orbital, here this point you have to remember, hybridized orbital always overlaps leads to give sigma bond. This is a very important point. Hybridized orbitals always overlaps leads to give the sigma bond. Clear? This s and p orbital, when they are overlapping or intermixing, leads to give the new hybridized orbital, right? These new hybridized orbitals are overlapping leads to give the sigma bond only. So the best example for you for the sp hybridization, the best example I was taking the BeCl2. Beryllium valency electronic configuration is, this is ground state electronic configuration of the beryllium is 2s2. Clear? Then when this beryllium is having the completely filled, but two chlorines are coming to form the bond formation. Two chlorines are forming the bond formation. Then what it will happen? This chlorine and this chlorine will be repel. Due to that repulsion, that energy will be utilized by the central atom of the beryllium and it will excite this electron to the empty orbital of the p. Then we call it this as a excited state electronic configuration. Now excited state electronic configuration, we are having the 2s and we are having the 2p. Done. Now this 1s and 1p will be intermix. These two will be intermix, leads to give the new hybridized orbital in this manner. Now each hybridized orbital we are having the 1 electron. Now these two new hybridized orbitals should arrange themselves in such a way that it should be free from the repulsion. Then these two new hybridized orbitals are arranged at the bond angle of 180. When these two new hybridized orbitals are arranged at the bond angle of 180, those are free from the repulsion. Clear? When at the bond angle of 180 degree. When they are arranged at the bond angle of the 180 degree, those are free from the repulsion, right? Sorry. Those are free from the repulsion. Now you see this hybridized orbitals. No. Now each hybridized orbital we are having the 1 electron. Each hybridized orbital we are having the 1 electron. And chlorine we are having the 3s2 3p5, right? One unpaired electron of the chlorine will be present in 1p. So the p orbital will be dumbbell in this manner. One p orbital will be in the dumbbell. Clear? Now this bond angle, this is a BeCl2, this is Be and this is Cl and this is Cl, and the bond angle between them will be the 180 degree. 180 degree. In this manner sp hybridization is forming. Now comes to the sp2. Here in the sp2 1s and 2p orbitals will be intermixed. 1s and 2p orbitals will be intermixed, leads to give the sp2. Example I was taking for the bf3 is the example. Now in this bf3 ground state electronic configuration of the boron will be 2s2 2p1. Then excited state electronic configuration of the boron will be 2s1 2p2. This after excited state, this orbital should be intermixed, right, to make the energy same. Then leads to give the new hybridized orbital. In this manner, each hybridized orbital we are having the 1 electron. Now these three new hybridized orbitals should arrange themselves in such a way that it should be free from the repulsion. Now these three new hybridized orbitals have arranged themselves at the bond angle of 120 degree. At the bond angle of 120 degree. When they have arranged, these are free from the repulsion. Then each fluorine will have the 1 electron in the p, right, f. 1s2 2s2 2p5. One orbital having the unpaired electron. This orbital, p orbital only, will be overlap with the sp2 hybridized orbital. So now another fluorine. Clear? Now here the another fluorine. Clear? In this manner sp2 hybridized orbital will be formed. Now this is the shape of the bf3. And the bond angle between these two is a 120, and the shape we got and the geometry we got it as a which one? Trigonal planar. Now here after that here we have seen, right? Now BeCl2 bond angle is 180 we got, and the geometry we got it as a linear. Now sp3 already we have seen. For the sp3 carbon, one hydrogen and the one hydrogen, and the bond angle is 109 degree 28 minutes. Clear? And the geometry we got it as a tetrahedral. Clear? Now all the three will study in the one page. First 1s 1p leads to give the sp bond angle is 180 degree and geometry is linear. Done. Next 1s 2p leads to give the sp2 bond angle is 120 and the geometry is trigonal planar. Done. Next 1s 3p leads to give the sp3 and the bond angle is 109 degree 28 minutes and the geometry, bond angle is 109 degree 28 minutes and the geometry is tetrahedral. Clear? Now based on this sp, sp2 and the sp3, how our organic molecule has been related, now we'll see.
Now we'll see how the hybridization is interrelated with our organic molecule. Now first I was going to explain you the hybridization of the sp3. Now hybridization of the sp3, the example I was going to take, that is C2H6, that is ethane. It is a ethane. Sir, for this C2H6 ethane molecule, if they are given, how you are saying this as a sp3? To identify the hybridization of the organic molecules hybridization to identify, we are having the hybridization is equal to number of sigma bonds plus number of lone pairs. If you remember this formula, you can identify the hybridization of that organic compound. Done. That for that one, we know C2H6. How the C2H6 will be there? One carbon valency is the 4. So now this carbon valency has been done. Then the another carbon, it is having the 3 hydrogens. Now this is the which one? This is the structure of the which one? Ethane. This ethane, it is having the 1 sigma bond, 1 sigma bond, 1 sigma bond and 1 sigma bond. Then number of sigma bonds for this carbon, it is 4 and the number of lone pairs are 0 for this carbon. So if the hybridization number is 4, then we call this as a sp3. If the hybridization number, if it is 3, then we call this as a sp2. If the hybridization number, if it is 2, that is sp. Clear? Then this carbon, we are having the number of sigma bonds are 4, so this is sp3. This carbon, we are having the 1 sigma, 2 sigma, 3 sigma and 4 sigma, and the hybridization is sp3. sp3. Clear? Done? Now, based on this hybridization, they will ask you, what is the, here we have seen this sigma bond, right? What is the overlapping between this carbon and carbon? How this, by which overlapping leads to give the sigma bond? And what is the overlapping between this carbon and the hydrogen? That we have to see. Then for that one, we know the carbon ground state electronic configuration is, for the valency I was writing directly, 2s2 2p2. Already I explained, only the valency electrons will be participated in the bond formation. So this is 2s2 and this is 2p2. Now for the excited state electronic configuration will be 2s1 2p3, 2s1 2p3. But the hybridization we got it is which one? sp3. Then sp3 means how many orbitals should be intermixed? Already I explained. 3 orbitals should be intermixed, right? So these 3 orbitals will be intermixed. These 3 orbitals intermixed leads to give the new hybridized orbitals in this manner. New hybridized orbitals will be in this manner, they will give. Each new hybridized orbital we are having the 1 electron. Now these 3 new, for this 4 new hybridized orbitals should arrange themselves in such a way that it should be free from the repulsion. In which bond angle it should be arranged? At the bond angle of 109 degree 28 minutes. If they are arranged, that bonds or this hybridized orbitals will be free from the repulsion. So now how they will arrange? Now you see, because this is for the another carbon also same, C2H6 we are talking, right? For the other carbon also we will get the 4 new hybridized orbitals only. So first hybridized orbital of the carbon, they will overlap in this manner. They will overlap. Done. Now here one hybridized orbital we are having the 1 electron. Now another hybridized orbital we are having the 1 electron. This is a carbon. This is a carbon. Done. Carbon. One hybridized orbital, one hybridized orbital. This hybridized orbital is which hybridized orbital? sp3, and this hybridized orbital is sp3, because 1s and 3p orbitals leads to give the new sp3 hybridized orbital, right? Hybridized orbital. Done. Now one hybridized orbital, but we are having the remaining 3, right? One has been done. Remaining 3 we have to arrange. Now remaining 3 hybridized orbital will be in this manner. One will be in this manner. Another will be in this manner. Now the another will be in this manner. Clear? Each 3 hybridized sp3 hybridized orbital we are having the 1 electron. Here also same. One hybridized orbital, one hybridized orbital, one hybridized orbital. Okay, we take the smaller one. Now, hybridized orbital. Each hybridized orbital we are having the one electron. Now, hydrogens, right? Hydrogen, it is present in 1s1. Now, in the s orbital we are having the electron. So, each s orbital will be overlap. Each s orbital will be overlap. Clear? Now, here this carbon and the carbon, this sigma bond is formed by the overlapping of sp3 and the sp3. Done. And 6 carbon and the hydrogen is formed by the overlapping of sp3 and s. Clear? Now, this they will ask. This they will ask. Total 6 carbon and hydrogen we are having, right? This is in this manner. This carbon and the carbon sigma bond has been formed by the overlapping of sp3 and sp3 hybridized orbital. Then remaining this 6, here 1 carbon 3 and this carbon 3. Total 6 carbon and hydrogen is formed by the sp3 and s. Here in this manner our ethane molecule will be formed and due to this overlapping it will be formed. Now you can see here, now I can show you. This is a ethane molecule, just now I showed you. Now, here 4 new hybridized orbitals should arrange themselves in such a way that free from the repulsion. One hybridized orbital, here one electron. This 1 carbon, this is 2 carbon. Now, hybridized orbital, this is sigma, and the remaining 3 here, and the hydrogen 1s. Clear? Now, in the real life, in the molecular level, how the ethane molecule will be there. Now, I will show you this. Now you can see. Now this is the ethane molecule. This is the ethane molecule. You can see these 2 blacks are the carbon. These 2 are the carbon. This carbon and the carbon sigma bond, and this carbon and the hydrogen. This is hydrogen. This carbon and hydrogen. This is a sigma bond. This is sigma bond carbon and hydrogen. This is a carbon and hydrogen. This is a carbon and hydrogen. This is carbon carbon sigma bond. This carbon and this carbon is formed by the overlapping of sp3 and sp3. Done. Now this carbon and the hydrogen is formed by the overlapping of sp3 and the s. Done. Now next we will move to the sp2 hybridization. Next we will move to the which one? sp2 hybridization. In the sp2 hybridization, now we are taking the example of H2 C2 H4. C2H4, right? Now in this C2H4, this is a C2H4. Now in this C2H4, we are having the 1 carbon carbon sigma bond, 1 carbon carbon pi bond, and 4 carbon hydrogen sigma or single bond or sigma bond. These carbon sigma bond is formed by the which overlapping? This carbon pi bond carbon is formed by the which overlapping? This 4 carbon hydrogen sigma bond has been formed by the which overlapping? Now we have to find. For that one, first we have to find the carbon hybridization. How to find this carbon hybridization? Already I explained it. This is 1 sigma bond, this is 2 sigma bond, and this is 3 sigma bond. This 3 sigma bonds hybridization will be sp2 because hybridization number will be equal to number of sigma bonds 3 and number of lone pairs 0 will be equal to 3, right? If the hybridization number 3 means that is sp2. Done. Here this is carbon hybridization sp2 and this carbon hybridization is sp2. Now comes here. Carbon ground state electronic configuration will be 2s2 2p2. Excited state electronic configuration will be 2s1 2p3. Now we know in the sp2 only 2 orbitals will be intermixed. Only one s and the 2 p orbitals will be intermixed. Now you see this another one p orbital. It is pure p orbital. Why it is pure p orbital? It has not participated It has not participated in a hybridization. It has not participated in the hybridization, right? So that's the reason this is a pure p orbital. This is a pure p orbital. Clear? Now, these three atomic orbitals overlaps leads to give the new hybridized orbital, right? Which new hybridized orbital? sp2. This sp2 hybridized orbital we got, and one pure p orbital is left. This pure p orbital is not participated in the hybridization. Now, these three new hybridized orbitals should arrange themselves in such a way that it should be free from the repulsion, right? At the bond angle of 120, when they have arranged, those are free from the repulsion. Now you see how they are arranging. One carbon, we are having the one electron. Now another carbon also we are having the one electron. Here this carbon and this carbon is forming the sigma bond. Already I explained you. Hybridized orbitals overlaps leads to give the sigma bond only. Leads to give sigma bond only. So hybridized orbital overlap leads to give sigma bond. One hybridized orbital, this carbon and this carbon, sigma bond. So this carbon and this carbon, sigma bond is formed by the overlapping of sp2, because this hybridized orbitals are sp2. And the remaining two also we are having, and the remaining two will be in this manner. They have arranged at the bond angle of how much? 120 degree. Now, at the 120 degree, when they have arranged, those are free from the repulsion. When they have arranged at the 120 degree, those are free from the repulsion. Now, hydrogen, it will be present in the S, right? Will be present in the S. So, this carbon and the hydrogen is formed by the overlapping of sp2 and S. sp2 and S. Now, you see, next we are having the one pure p orbital is left, right? This one pure p orbital is left. This pure p orbital is perpendicular to the hybridized orbital. This point is very, very important. Pure p orbital which has not participated in the hybridization is perpendicular to the hybridized orbital. This pure p orbital is a perpendicular to the hybridized orbital. So this carbon, it is having one pure p orbital, and this carbon is also having the one pure p orbital. Now it is having one electron, and these two, for this hybridized orbital, this pure p orbital is perpendicular, right? These two sideways overlaps leads to give the pi bond. This sideways overlap leads to give which one? Pi bond. So this carbon and the carbon pi bond is formed by the overlapping of pure p and the pure p. Now we'll see now how the pi bond will be, or how the ethane will be formed. Now we'll see. Now here experimentally this is the ethane molecule. Now in this ethene molecule, this is the ethene molecule. In this ethene molecule, this is the one carbon and this is the one carbon. Now one sigma bond and one is a pi bond, and this carbon and the hydrogen, and this is the carbon and the hydrogen. This is the carbon and the hydrogen, and this is the carbon and the hydrogen. Now this is the ethene molecule. One sigma, this sigma bond is formed by the overlapping of sp2, and this carbon and hydrogen is formed by the overlapping of sp2 and the S. Clear? And this pi bond is formed by the overlapping of which one? Pure p and the pure p. Done? Pure p and the pure p, it has been formed. Now you can see here with the orbital diagram also. Now you can see here, this is a carbon with the sp2 and sp2 formed the sigma. Another sp2 hybridized orbital and s orbital, another sp2 and the s, another sp2 and the s. Clear? And the pure p orbital is perpendicular Pure p orbital is perpendicular to the hybridized orbital. Now sideways overlap leads to give the pi. Sideways overlap leads to give the pi. Then you can see here this R will be at the bond angle of 120. Now this pi bond is perpendicular to the hybridized orbital. Hybridized orbital. In this manner it will be there. Now this is about the which one? About the ET. Now next we are going to talk about the SP. Now in this SP directly I will explain here with the SP. Now in the SP now in this SP molecule we are going to talk about the ethane, right? C2H2. In this C2H2 carbon triple bond carbon and hydrogen. Now here this hybridization of this carbon is sp, this carbon hybridization is sp. How? 1 sigma 2 sigma, hybridization number is 2. If the hybridization number is 2, that is sp. Then in the sp excited directly I was writing directly carbon excited state electronic configuration, if I write 2s 2p3, then only 2 orbitals will be intermixed for the sp, one s and the one p. They will give the new hybridized orbital is in this manner. In this manner they will give. So for the sp hybridization, 2 pure p orbitals we are having. Pure p orbitals we are having 2. Pure p orbitals will be having. Pure p orbitals means nothing but they have not participated in the hybridization, and these pure p orbitals will be perpendicular to the which one? Hybridized orbitals. Now you see one sp and another sp leading to give the 1 sigma. This sigma bond is formed by the overlapping of sp and sp, and this sigma bond is formed by the sp and s, sp and s, and 2 pi bonds we are having, right? These 2 pi bonds are formed by the which one? Pure p and pure p. This is p and this is p, this is p and this is p. In the ethyne, 2 pi bonds are formed by the which one? Because these 2 pure p orbitals are not participated in the hybridization. The p orbitals electrons which are not participated in the hybridization, those are forming the pi bond in the organic molecule. Those are forming the pi bond in the organic molecule. Now you see, in this case of the which one? Ethene case also, pi bond is formed by the pure p orbital only. In the ethyne case also, this pi bond is forming by the pure p orbital only. What is the meaning of the pure p orbital? Which has not participated in the bond formation is known as the pure p orbital. Clear? Now already we have seen the alkane, alkene. Now we will see the structure of alkane. Now in this structure of alkane, now you see here this carbon and a carbon, one sigma bond. This is a sigma bond. It is formed by the overlapping of sp and sp, and this carbon and the hydrogen. This sigma bond is formed by the overlapping of sp and s. Now you see these 2 pi bonds it has been formed. These 2 pi bonds has been formed by the which overlapping? Pure p orbital, right? Which are perpendicular to the hybridized orbitals. Now that leads to give the linear molecule. This is sp. sp is the linear, right? Here you can see this is a ethyne molecule. Ethyne molecule will be in this manner. Now by that I was ending the class, and the remaining we will see in the next class. See you in the next lecture.